So welcome to the first lecture of the course Functional Programming in Haskell. So functional programming starts with the point of view that a program is a function. Abstractly, a function can be thought of as a black box that takes inputs and produces outputs. In other words, a program is a function that transforms inputs to outputs. So when we write a program in a functional programming language, what we are doing is specifying the rules that describe how to generate a given output from a given input. And when we compute in a functional programming language, we apply these rules to the input that is given to us in order to actually produce the output that is expected. So the first thing we have to ask ourselves is, how do we build up these programs? Now it's impossible to start from nothing. So we have to assume that we have some built-in functions and values. Right? So we assume that we begin with something that is given to us, and then we use these built-in functions and values to build more complex functions. So let's look at a concrete example. Suppose we start with the whole numbers, that is the integers 0, 1, 2 and so on, so the non-negative integers. And suppose the only thing that we know how to do with these numbers is to add 1. So we have a successor function which we can think of as a +1 function. So it says that 0 plus 1 is 1, the successor of 1 is 2, so 1 plus 1 is 2 and so on. Right? So this is what is given to us. We have the whole numbers and the successor function. Note, by the way, that we have used a slightly non-standard notation for the functions. Normally one would write successor of 0 with brackets like this, so we write f of x normally. But in functional programming, we will see that we will normally write fx, eliminating the brackets. So this has two advantages. One is you have fewer brackets to worry about, but it also has some interesting technical advantages which we will describe in a later lecture in this week. So now that we have the successor function, we can apply it twice to an input, for example, and get a new function which adds 2. So plus 2 of n takes n, applies successor, and then applies successor to that. So it's as though we had two boxes with us called successor. Right? So we feed n here, then we get n plus 1. We feed it to the second box and we get n plus 2. And what we are saying is that now we can take this two boxes and call this outer box plus 2. Right? So this is what it means to compose two functions. You take the output of the first function and feed it to the second function. So in this case, we have composed the same function twice. We have taken the successor of successor. However, we can also combine two different functions. For instance, we can take the plus 2 which we have defined and feed its output to successor. So we have plus 2 and now we have successor. So we already know that if we take a number n and feed it to plus 2, we get n plus 2. And then we feed it to successor and we get n plus 3. And now this gives us a new box which we call plus 3. Right? So in this way, we can combine functions by function composition, which is well known to us from mathematics. But now suppose we want to extend our definition of plus 2 and plus 3 to plus 4, plus 5, plus 6. In general, we want to define plus with two arguments, n and m, where we mean that when we say plus nm, we apply successor to nm times. In other words, we start with n and then we do plus 1, and then we do plus 1, and then we do plus 1. And so totally we add n m times, 1 m times. Right? So this is what plus means, and this is how we were, if you remember, this is how we were taught the definition of plus when we were in kindergarten. You just keep adding 1 by 1 by 1 m times. So how would we describe this in our setting? Because we need to describe this family of plus ones. So by the way, again, note this notation. We don't write a function of two arguments with brackets as usual, but we just write the arguments one after the other. So plus followed by the first argument, followed by the second argument. You can just think of it right now as a peculiar syntax which eliminates argument, brackets and commas. But as we will see, this is a very interesting way of thinking about functions from a computational standpoint. So what are the rules for plus? Well, we know that plus n1 is the same as successor, the built-in function that adds 1. Plus n2 is, we have seen the successor of successor, but we can think of successor of n as plus n1, right? So we are taking plus n1 and then applying successor to that. So in the same way, plus ni, as we saw before, will apply the successor I times. And the question is, how do we write a rule which captures this mysterious dot dot dot, which says do something a fixed number of times, but that fixed number of times depends on the value of the argument. So this brings us to the realm of inductive or recursive definitions. So an inductive definition is one where we specify a base case and then we specify the value for larger arguments in terms of smaller arguments. So for instance, we know that if we add 0, then we do nothing. So plus n0 is always n. So this is the base case. We don't have to do any computation. We just return the first argument. Now plus n1 consists of adding 1 to n. But we can also think of applying the previous value 0. So we get plus n0. So we just don't think of it as n, but we think of it as the base case. And now we apply successor to the base case. Similarly, in general, if I want to add something to m plus 1, then assuming that I know how to do n plus m, then I can add 1 to that. So this is just saying that the value of n plus m plus 1 is the same as the value of n plus m, which I know how to do inductively, plus 1, which is given to me. So this is my given function. Okay. So this is the basis of inductive or recursive definitions, that you take a base case whose value is obvious, and for larger values you describe it in terms of operations that you know how to do, plus the operation you're trying to define on smaller values, which is inductively known to be true. So how does computation work? Well, it just unravels the definition. So supposing I want to add 7 to 3. Now in our universe we have 0, 1, 2, etc. and we know that successor of 0 is 1, successor of 1 is 2, and so on. Right? So I can think of 3 not as 3 but as successor of 2, and now I have a rule which says plus, if you remember the rule, it says plus n successor of m is equal to successor of plus n m. This is the rule that we wrote. So if I have plus 7 successor of 2, this is successor of plus 7 2, where I plug in 7 for n and m for 2. Now once again I can expand this 2 as successor of 1 and apply that rule again, and I get successor of successor of plus 7 1. And then once again I can replace the number 1 by the expression successor of 0, and then I get successor of plus 7 0. Now this is the base case, which is 7, right? So I get successor of 7, and then if I continue with this computation, this will give me 8 by the built-in rule, this will give me 9 by the built-in rule, and this will give me 10 by the built-in rule. So this is how I will get plus 7 3 equal to 10. The important thing to note in this is that computing the value 10 does not involve understanding anything about numbers. It is just syntactically replacing expressions by expressions, and this is something that we will see more formally later. So this is how computation works in a functional programming language. You have rules which tell you how you can replace one expression by another expression, and you keep replacing expressions until you reach a value which cannot be simplified. So let's look at another recursively defined function. So just as addition is repeated application of the successor function, multiplication, as you may remember from school, is repeated addition. When I say multiply n by m, it means add n to itself m times. Right? So we have to apply plus n m times starting from 0. So the base case says that if I multiply any number by 0, then I will get 0. Right? So multiplying, so this is not n but 0. So multiplying n by 0 is 0 for every n. And now n times m plus 1 is just n plus n times m. Right? So this is the inductive case. I know how to do this because this is smaller. Okay? And this is now a known function because we have already defined plus. So plus was not a given function, successor was the given function, but we have already defined plus in terms of successor. So now we can use plus to define multiplication. So to summarize, a functional program describes rules to tell us how to compute outputs from inputs. What we have seen is that the basic operation that we use is to combine functions. So we use function composition. We feed the output of one function as the input of another function. And now often we have to apply this function composition more than once, but not a number of times we know in advance. So when we did +2 and +3, we knew exactly how many times we had to compose a function. But when we wrote a general plus or a general multiply, we had to apply these functions depending on the value of the argument. So for such functions, we saw that recursive definitions are a good way to capture the dependence of the number of times the function has to be composed based on the input value.